So you really kind of like need to know this stuff in order to appreciate how many bonds things form, the concept of valence, etc., etc. But before we get started with chapter, hello.
Hi.
Let's talk just a little bit about the lab that we did. There were only a few parts of the lab. They're fairly simple, and they basically deal with lab skills and with doing very simple calculations. First thing you did was to read a meniscus in a couple different types of graduated cylinders. This one, for example, that's 6, that's 7, that's 8. So every little line here is 0.2. Now the thing that we said was that when you read a concave meniscus like this, so it's concave down, what you do is you sight directly at the very bottom of this thing. So when you do this, you'll be reading it just about there. Now as I look at this, that's 6, that's 7, so that's 6.6, and it's just a touch above 6.6. So in this particular graduated cylinder, I could read this at about 6.62. So down to 100th of a milliliter. This is a much larger graduated cylinder. Again, here's our meniscus. So we want to read right here at the bottom. Now this is 50, 55, so everyone is 1. So that's 51, 52, and that would be 53, and it's just shy of the 53. I'd probably say something like 52.8. Now this is for a negative meniscus, also called a concave. There's another type. The reason that water forms a meniscus like this in glassware is that the glassware, the actual structure of the glass, is charged, very polar. So is water, so it kind of climbs up and hangs on to it. Something like mercury is very phobic from those types of surfaces. So in a mercury meniscus, you actually have a positive meniscus like this, where it's minimizing. A negative meniscus, you read the bottom. A positive meniscus, you read the top. Any questions? We also did some measurements. And when you did these measurements, there were numbers that you had to deal with. And this is just a little slide that basically reviews rounding numbers, just to make sure we all understand the rules. We are going to round this number to 3 significant figures, so that's 3 digits. If the digit removed is more than 5, the preceding digit is increased by 1. So 378 rounds to, 379 rounds to 538. 3 significant figures, 3 digits. If we're going to remove a digit, so we're going to round this to 3 significant figures. If the digit we remove is less than 5, it disappears, and that goes to 241. Most people get that. The rule that most people don't know is what happens if the digit that you remove is exactly 5? Well, if the preceding number is odd, it's going to increase by 1. It's unchanged if it's even. So here we have 7, 5. 7 is an odd number. So this is going to round up to 8. Over here we have 6, 5. That's an even number. Even numbers round down. So that's 7/6. By doing this, when it's exactly 5, it always winds up that one compensates the other. So these rules are trivial. We all know how to do these. This rule here is a little tricky. Most people haven't heard of it. Any questions? There was a question on your lab about precision. Precision and accuracy. Precision and accuracy are two different things. Accuracy is a measurement of how closely an experimental value is to a known value. Precision is how reproducible a given value is. All right, so let's start off with my dartboard here. We're obviously aiming right here at the middle. Our first set of darts. Well, this is neither precise nor accurate. So if we had a measurement like this, this would be basically a bad measurement. They're just scattered everywhere. Here we have a very precise measurement. They're all grouped together here in the same spot, but they missed. So they're very precise, but they're not accurate. Precision tells you how reproducible something is. Accuracy tells you whether you hit the bullseye. Something like this, where we put them all, is both precise and it's accurate. So big difference between precision and accuracy. A measurement can be very precise, but not accurate. Let's look at this in terms of a simple density example. When we talked about density, I said that density of water at 25 degrees was 0.996, something like that. Okay? Here we do a simple measurement. We have 25 cubic centimeters, 25 degrees. We measure it at 24.9 grams. Remember, density is mass divided by volume. Therefore, we do our simple calculation here, and we get 0.996. It's a single measurement, but it's very accurate, isn't it? Because this is the known value, and we hit it right on the nose. Very accurate measurement. Here's just a simple example. Here we're measuring the mass of 25 grams of water, and it should be right along this thing. If we did this 4 times, and the numbers we got, 4 totally different measurements look like this, we'd be very happy because these all cluster right around the known mark. And so this measurement is both precise and accurate. If we did this and we got a whole bunch of measurements way up here, but we know the answer is here, these are precise, but again, they're not accurate. Now, this is called systematic error, and this could be like there's balances you've not calibrated right or something. So you're doing it right, everything is right, but there's something wrong. Here we have a bunch of data points, and numerically, if you were to take these and take their average, it would wind up right at 25. But if you look at the data, it should upset you and say, well, that's ugly. The average is very good, very low precision, but the average is accurate. And the opposite of that is something like this, where we have both low precision and low accuracy. Average would be up here somewhere, our precision is bad, and the accuracy is bad too. Any questions on the concepts there?
I have a question. These slides that you just showing us,
What?
were those the slides that you just showed us?
Yeah.
Were those to be printed?
No, I just made them like an hour ago.
Oh. Okay.
We also did density in this lab. If you like, I'll put the set of slides up on Blackboard.
Yeah, because that was a
Yeah, you can print them. When we talked about density, we said it was simply mass divided by volume. One concept I want to make sure everyone knows is that a liter is 1,000 cubic centimeters, and that 1 milliliter is exactly 1 centimeter. Remember that, those are important. Well, in the experiment we did, just for an example, if we have 1 cubic centimeter of gold, it's 19.3 grams, so our mass is 19.3, our volume is 1, and that's our density. All right, very simple little equation. Problem that we had in lab, we had a bar that was, so long, so wide, and so high, right? First thing we did was to weigh it. Let's pretend that it came out to be about 73 grams. So that's our mass. Our volume is simply going to be length, width, and height. So if you take this and plug in our numbers, multiply it all together, our volume here is 7.776 cubic centimeters. Now that's the calculator answer. That's not right, is it? Because look at our measurements. These are only 2 significant figures, aren't they? So the volume cannot be more accurate than 2 significant figures. So we just have to round this. We're going to round this to 2 figures. So our 7 is going to round to an 8. All right, so we know our mass and we know our volume. We're going to take those, calculate our density. Mass divided by volume. Here's our mass, here's our volume. This again is our calculator answer. Now, how many significant figures do we round to? 3. When you look at your problem, we have 3 up top, don't we? But only 2 in the bottom. So it can't be any more accurate than 2.
Also, even if there's 3 in 1 or 4 in 1, it has to be the smallest.
Right, it's got to be the smallest one. So we're going to round this to 2 significant figures, and that's 9.4. Any questions? Now, a point that I tried to make in the lab, when I was talking to folks, was that when we did a density like this is of whatever metal that bar was made of. It's a physical property that's inherent to the metal, not the bar. So it's independent of the size of your sample. Simple way to think about this. Instead of weighing 1 or measuring 1, what if we would have done 2 bars? Okay? We'll say they're exactly the same. So we did 2 bars, right? So instead of 73, our mass is 146, twice that, right? Our volume for each of these was 7.8. We just did that in the previous slide. So our density is going to be our mass here, and we're going to divide it by our total volume, 7.8 for each one. And if you do this calculation, by gosh, it turns out the same. So it's independent of your sample size. And the last thing we did was the Archimedes experiment. Instead of using a rock, we used a stopper. The same thing. Let's just make sure we understand the calculations here. Started off with a graduated cylinder with water. And we put everything in. We recorded where the volume was initially and where it was finally. To calculate the volume of the rock, what we did was simply subtract the final from the initial, and that volume represents the volume displaced by the water. So, same equation. Our mass was 43. Here's our difference in our volumes. And all we have to do to calculate the density is a simple division. 1.86 grams per mil, which of course, remember, is the same thing as 1.86 grams per cubic centimeter. Any questions?
Yeah. What are they?
You got it? Okay. All right, well, let's go ahead and start on chapter 2. Some of the stuff in chapter 2 we hit on in chapter 1. We'll just review it lightly and then go a little bit deeper into the subjects. Remember, we talked about the classic atomic structure of atoms. We said that there was a nucleus and there were electrons. The nucleus is in the middle. The nucleus will be positively charged, and the electrons are negative. This is a classic Jimmy Neutron version of the atom. Of course, it's not right. Quantum mechanics tells us that the nucleus is much, much smaller, and that the electrons are not in orbits, but they simply occupy a region of space. This represents an atom of helium. Here in our nucleus, we have 2 protons and 2 neutrons, and we have 2 electrons surrounding it. So we have 2 positive charges here in the middle, and 2 negative charges outside. And that means that this is a neutral atom. 2 pluses, 2 minuses. Now, all of this is very, very small. We said that in a real copper penny, you would have roughly 28 sextillion copper atoms. Now, that's a huge number, huge number. The mass of a proton is just the opposite. It's a very, very, very small number. This is 10 to the minus 24 grams. Now, we talked about scientific notation. Remember that 10 to the minus 24 looks like this, with 23 zeros in front. Move our decimal point right in there. That's the mass of a single proton. Now, a neutron weighs essentially the same thing as a proton. Again, it's about 10 to the minus 24. And an electron is much, much less. Now, that means that the mass associated with an atom is virtually 100% in the nucleus. So think about your picture of the atom. We have a nucleus here that's so small it doesn't show on the screen. And yet that is the entire mass of this atom. But even this picture that I've drawn here is distorted. Let's look at something a little more familiar. This is Wrigley Field, and that's a golf ball. Let's pretend that the golf ball is the nucleus, not just a typical atom. Well, if this was the size of a nucleus, and you put it here on the infield, basically the electron cloud surrounding it would be all the rest of Wrigley Field. So atoms are essentially totally empty space. They have this little nucleus in the middle that weighs, and then you have this electron cloud, very, very diffuse electron cloud. Any questions? All right, we talked about elements too. We said an element was a pure substance that contained only one type of atom. We said that every element would be identified by a chemical symbol, and that chemists tended to arrange elements according to the periodic table. Now there's a periodic table, it's a little dated, but it's still a periodic table. When periodic tables didn't always look like this, as they were developed, or when they were developed, people knew enough about elements and compounds that they could calculate the mass. And what people did was to start to group elements according to their reactivity. An example, M here stands for a metal. Turns out that there's a group of metals that will react with oxygen to form metal oxides. Now this is a chemical equation. Remember what we said, we must have the same numbers and types of atoms on both sides. So here we have 4 metals. Here we have 2 times 2, that's 4 metals. 2 oxygens, that's 2 oxygens. So same numbers and types, and same mass. When I say that these metals reacted in a similar way to give this product, M2O, they did, but they all had slightly different inherent reactivities. Now this is actually a cute little slide. This is lithium, sodium, and potassium. And what the guy's doing in these is putting the metal in the water. And as you see, lithium, when it hits water, reacts. It fizzes, bounces around a little bit. It's not real exciting to watch. This is sodium. If you take a chunk of sodium and you put it in water, it's a little more interesting because as the reaction goes, the sodium gets hot enough that it totally melts into a little sphere bouncing around the surface. If you had a big enough chunk, you could actually get an explosion out of it. And we saw this last time. This is potassium. Potassium, when you put it in water, reacts much more vigorously than either of these two. In fact, it gets so hot that the hydrogen gas that's formed burns spontaneously. So it was observed that these metals all gave M2O, but they had different inherent reactivities. The very first periodic table was published by a Russian chemist, Mendeleev, and it looks something like this. Now, Mendeleev misspelled table. And you know, this is supposed to be group. We'll see that in a minute. But if you note here we have lithium over sodium over potassium. And over here on today's, lithium, sodium, potassium. So they got the ordering right, just simply based on chemical reactivities. Chemical reactivities tend to define these groups, yeah.
Will they always be compatible with the periodic table?
Well, this is the type of periodic table we'll use. We'll see in a little bit that there are different types.
Okay, so that won't always be in order. You know,
They will always be in order for you. Yes. But there are unusual periodic tables. This is the one that represents this thing here. Again, this is a little outdated. Row 7 here has now been totally filled in. They've discovered these synthetic elements. Even though they haven't been named yet, they do finally exist. But this is a classic periodic table. And hopefully by the end of today, we'll be able to understand why it looks like this. Kind of a funny looking arrangement, but there's a real logic to it. Now, every element in the periodic table has a symbol. For many elements, the symbol is very simply a derivative of the name. Hydrogen, beryllium, magnesium, M and G, carbon, helium. But remember that there's a lot of these guys at the bottom here especially that have symbols that are based on the Greek or Roman names. So those are just a little tough. We looked at a starter list. Again, make sure that you pretty much know these things. These are the ones we talk about. And like I said last time, when we talk about things in class, those are the kind of things that I'd like you to remember. We talk about sodium. Where's sodium? Here, Na. Everyone should know sodium is Na. Okay? Simple. And the same thing with as we do things, blah, blah, blah. Some of the elements down here are tough to remember. We're not going to deal with those. But the ones that are common that we talk about, please try to know those. All right, just like Mendeleev did, we're going to group, or we're going to arrange our periodic table in terms of groups and periods. The groups go vertically, and the periods go across. Now, you'll see that 1 through 8 are numbered. That's just like Mendeleev had. But all these guys in the middle are missing. If you actually look at this periodic table, you'll see that it has 2 sets of numbers, the 1 through 8, and these things are labeled with B's. Some tables number them 1 through 18. There's a real advantage to sticking to the 1 to 8. And when we start doing things like Lewis structures and talking about valence and stuff like that, it'll become very clear to you why 1 to 8 is a good deal. So we're going to do groups 1 to 8. The periods, as you go down, we'll see by the end of lecture the quantum level where the electrons live in that particular collection of elements. But that's getting ahead. Let's just start off by taking our periodic table and using it as a grid. If I ask you what atom was found in group 1, period 4, well, that's pretty simple. We find group 1. Go down to our 4th period. We're here with K. Remember what K is? One that you need to know.
Potassium.
K is potassium. Group 2, period 6. 2. Go down to our 6th period. We're at BA. BA was on our starter list. It's based on the English name, and it's simply barium.
BA or BE?
BA.
I think it says BE.
BE is beryllium. That's over there. That's
So it's in
period
BA?
2, group 2.
I don't see it on their starter list.
Oh, you don't?
No.
Okay, add it.
What, how you
That's
spell
our first edition then.
variant?
Barium, right.
How you spell?
B-A-R-I-U-M. BA. Barium sulfate is commonly used in medicine, so something you need to know. We're dealing with group 8, period 4. So group 8, we're all the way over here. Period 4, go across. There we are with Kr. That's krypton, not kryptonite, it's krypton. Any questions?
That's supposed to be on our starter list too.
Well, again, if we talk about it, you should know it. Everyone knows Superman.
I didn't know KR is Superman.
All right, these are some old test questions, just so you get a feel for how you can ask questions about something as simple as element symbols. We're looking for the symbols for silicon, arsenic, bromine, barium, and cobalt. Now, some of these we've talked about, some we haven't. Well, silicon is a very simple one we have. Silicon is an Si. So as I look at this list, Si we have B, C, and D, they're all good. Okay? Arsenic, right now we have no idea. It's either As or Ar, isn't it? Barium, bromine. Bromine is on our list. Bromine is a Br, isn't it? Oh, but they're all Brs. We just did barium. That's a Ba. Oh, so we're either B or C. And finally, cobalt. Well, cobalt wasn't on our list, but chlorine was as a Cl. So that means that has to be wrong. Arsenic is As. Ar is argon. Which of these has a symbol with 2 letters? Fluorine, phosphorus, oxygen, silver or nitrogen. Remember at the bottom of the periodic table, we plucked out silver and said, gee, that's unusual. It's an Ag. Fluorine is an F, phosphorus is a P, oxygen is O, and nitrogen is N. What's in A? Everyone knows that. That's our friend sodium. All right, just another list. Copper, chlorine, cobalt, carbon, and cadmium. See if you can make some sense of this. Copper is either, obviously, Cu or Co. Chlorine, well, we know what chlorine is. It's Cl, isn't it? So we have 3 Cls here, but that doesn't clarify that. Cobalt, well, we just did cobalt. That was on the previous slide, wasn't it? That's a Co. Carbon, well, we know carbon's a C. Cadmium is a Cd. And B is our correct answer. And our last very simple one here, which of these only has 1 letter? We said the answer on the slide before the last one. Iron is Fe, antimony is Sb. No, it's Sm. Yeah. Tin is Sb, sodium is Na, phosphorus is P. Any questions?
How many slides were on this email?
How many slides?
Yeah. I didn't get any. I only got 3 pages.
No, I think there were 8.
I don't know.
Oh, here is one more, potassium. Potassium, we all know, of course, is a K. Now, when it comes exam time, I assure you, you will hope that there's a whole lot of these types of questions, right?
Hope so.
Right.
Same old thing.
Okay.
All right. As you look at the periodic table, if you look, every element and every symbol is arranged in numeric order, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 blah. Well, that's the atomic number for an element. What it means physically is that that is the number of protons in its nucleus. Now, this is a very, very important point. Any element, any substance that you have, anything, if it has 6 protons, it's a carbon. Doesn't matter how many neutrons it has, doesn't matter how many electrons it has. If it has 6 protons in its nucleus, it's a carbon. So this is the atomic number. All the elements here are arranged in order of the number of protons in the nucleus. We can write what's called an atomic symbol. The atomic symbol contains the symbol of the element. It contains the atomic number, that's the number of protons, and it contains something we call the mass number. Now, the mass number is simply the number of protons plus neutrons. Remember, we said that virtually all the mass in an atom was made up of protons and neutrons. So that's the mass number, simply the sum. So we're going to write an atomic symbol. We start off by writing the symbol for the element, whatever it is. Next thing we do, we write the mass number in front of the element symbol as a superscript. Remember, the mass number is number of protons plus neutrons. And finally, as a subscript in front, we write the atomic number. Now, this is going to become very important when we look at radioactivity, because when we talk about radioactive elements, we use atomic symbols all the time. So let's just very quickly write some atomic symbols for these guys. Here's a little data table. Number of protons, that's the atomic number. Number of neutrons. What I'd like you to do is to write atomic symbols for all these guys. Now, in case you don't know your list yet, hydrogen is H, lithium is Li, helium is He, and beryllium is Be. So you write the symbol. As a superscript in front, you put the mass number. That's the number of protons plus neutrons. And as a subscript, you put the number of protons. So hydrogen looks like this. Mass number of 1, atomic number of 1. Go ahead and do lithium. Lithium is Li. Mass number of lithium. We have 3 plus 4, that's 7. Atomic number is 3, that's our subscript. And it should look like that. Helium. 2 protons, 2 neutrons. Our symbol is He. 2 plus 2 is 4. 2 is our atomic number. And it looks like that.
So the atomic is the proton?
Now the atomic number, that's the number of protons in the nucleus.
I know, but where are you getting the other 2 protons?
We
'Cause
have
I see the neutrons.
2 protons, 2 neutrons, 2 plus 2 is 4.
Oh, because it says atomic number.
Atomic number is here. That's number of protons. And this is number of neutrons.
So atomic is the same thing as proton?
Right? Yep, remember that. That's important.
Like it's just flying over my head.
Beryllium. 5 plus 4 is 9. That's our mass. And 4 is our atomic number or number of protons. All right, let me hush for a second. And you do this at this higher math. Our atomic symbols, in case you've forgotten, oxygen is O, carbon is C, potassium is K, and iodine is an I. Starting with oxygen. 8 protons, 8 neutrons, that's 16. And the atomic number is 8. Potassium. 19 plus 20 is 39, isn't it? And our atomic number is 19. Carbon, 6 and 6 is 12. With 6 of those being protons. And finally, iodine. Nobody pulled out their calculator.
127.
It's 127, yes it is. 127 for our mass, 53 for our atomic number. All right, let's look at a couple test questions as to how this has been tested in the past, okay? Mass number of argon, argon is Ar, is 40, okay? We want to know what period it's in, what group it's in, how many protons, how many neutrons, and then write the atomic symbol for me. All right, first thing you have to do is find argon. Oh, there it is. All right, what's the little number there above argon? It's 18. And that's its atomic number, right over there, 18.
So the top number is
The atomic number of protons.
or protons.
That's atomic number. All right, first of all, let's do A. What is our period? Well, that's simple. We're 1, 2, 3, right? What group are we in? All the way over here for group 8. What's our atomic number? 18. So how many protons are in the nucleus? 18. Now, if the whole nucleus weighs 40 and 18 of those are protons, how many neutrons? Sure. 22. And so we write our symbol. Our chemical symbol AR. Our superscript is our mass number, that's 40. Our subscript is our atomic number, that's 18. And it looks like that.
How did you come up with 22?
Well, the nucleus weighs 40. 18 of those are protons. 40 minus 18? 22.
And if we have to write the number 8 in Roman numeral?
I don't
Or
care.
8 is, then it's what 8.
I can read both. All right. Let me hush for a minute. And you see if you can fill this one in. I'll give you a little preamble. The key thing to this is that this is a neutral element. Now, what do we say about a neutral element? Remember?
Same amount of electrons and
Same amount of electrons and protons. Okay. In order to be neutral, you have to have the same number of positives and negatives. If it has 12 electrons and it's neutral, it has 12 protons, right? So its atomic number is 12. You look at your periodic table and you find number 12. And by George, it's magnesium. So go ahead and fill in the rest. Magnesium is here in what period? 1, 2, 3. It's in what group? Our second one. How many neutrons? Well, if it has 12 protons and it weighs 24, it's 12. So our mass number is 24, our symbol is Mg, number of protons is 12, and that's magnesium.
You have electrons up there. What is,
That's,
So-
remember the key word here is neutral. In order for something to be neutral, it has to have the same number of positives and negatives. Electrons are negatives, protons are positives, neutrons are neutral. So if it has 12 electrons and it's neutral, it must have 12 protons. Now, this brings us to the tutorial for today. The tutorial for today is called Protons. Is it here? No, it's not on this page. Protons, electrons, and neutrons. There it is. What this tutorial does is it gives you a partial table, and you simply fill in the rest. All right, let's start off with Sn. That's 10. So let's do this one together. Get our periodic table, and let's find 10. 10 is down here.
Where do you get 10 from? Where you get 10 from?
Sn.
Okay.
It's also over here, right
There.
there.
Print on the table.
I know, this is so tiny, I can't even see. 10.
10. 10. Metal. 10. 10 can.
Oh, I thought it was like 10.
Nope.
But that says 50 or,
Yeah.
I'm,
Tin can.
so 10.
All right, so we're down here at 50. So how many protons are we going to have? 50. If the atomic number is 50, we have 50 protons. Now we're also told that we have 66 neutrons. So what's our mass number going to be? It's going to be 50 plus 66. Now, here's the tricky part here. The charge here is +1. What does that tell you? That means it has one more proton than it does electrons. So if it has 50 protons, it must have 49 electrons. So atomic number is 50. 50 protons. Mass number is going to be 50 plus 66. If we have a charge of +1, that means we have one extra proton. So how many electrons? 49. Now isn't that one fun? This is fun. Go ahead and do this one for bromine. Bromine is right there. First thing you want to do is find bromine on the periodic table and find its atomic number, right? Well, bromine is here. And what is it? It's a 35. Now on every exam, you will get your very own copy of your periodic table. So it's something to look forward to. All right, so we're at 35 here. So that's 35 protons, right? If we have 44 neutrons, what's our mass? Sure, it's just the sum. And if we're dealing here with a charge of -1, that means we have one extra electron, right? So if we have 35 protons, we must have 36 electrons. Atomic number 35, 35 protons. Mass number is simply the sum of those. We have one extra electron, so it must be 35 plus 1, 36. Let's do one more. Everybody's friend, uranium-235. This is what you use to build a fission bomb. So you look at the periodic table here. Anybody see uranium?
92.
Yeah.
No, it's not there.
92.
Because this periodic table doesn't have the bottom two rows, does it? Uranium is all the way down here. So we look over here, we find it's a 92. Go ahead and fill in the rest of the numbers. We have 92 protons. We are given that we only have 92 electrons. Electrons and protons are the same, aren't they? What's our charge? Oops. Well, it's a 0. Add those two up, you get, or subtract them, you get 143 neutrons and a charge of 0.
So we do have to put a 0.
Oh yeah, gotta put a 0. Any questions? As always, work 5 of them and get your points. All right, we all now understand that the number of protons in the nucleus tell us exactly what atom it is, right? Yeah.
I'm sorry. How did you get the neutron 143? Did you add?
Well, our atomic number was 92.
Uh-huh.
We were given the mass number. So we simply subtract those and 143.
Thank you.
All right, so the number of protons in a nucleus defines what element it is, right? So this is carbon. Carbon has an atomic number of 6, and the common carbon that we have has 6 neutrons as well, so a mass number of 12. Okay, everybody happy with that? We have electron clouds here, and the electron cloud is actually in 2 levels, but it has a total of 6 electrons. 6 protons, 6 electrons. Okay. If I took and wrote an atomic symbol here for carbon, I would do it this way. I would say mass number of 12, atomic number of 6, right? But what would happen if I put an additional neutron in this nucleus? Now our mass number would be 13. But we still only have 6 protons. Therefore, this is a carbon, isn't it? It just weighs more.
It's still a carbon? Does it change?
Still a carbon. Anything with 6 protons in its nucleus is a carbon. Period. If we add another neutron, we get something with a mass number of 14, but it's still a carbon. In chemistry, we refer to these guys as isotopes. They have different mass numbers, but they're the same element. Every element that is known exists as a collection of isotopes. For any one element, they'll all have the same number of protons, but you'll have different types that have different numbers of neutrons. If you actually look at the abundance of the isotopes of, say, carbon. Roughly 99% of carbon atoms are carbon-12. Roughly 1% is 13, and a teeny tiny trace is carbon-14. You've probably heard of carbon-14 from dating. That's how they can date artifacts that are, say, 10, 20,000 years old. They find carbon-14. We'll actually talk about that in that chapter. Because all of these isotopes have different masses, it's important that we know the distribution so we can calculate the average mass of carbon. You do that by this simple equation. We're going to convert the percentage to a fraction, multiply it by the mass. I didn't put 14 in here because it's too small. But you multiply these together, add them up, and you get this number. If you look at the periodic table, the numbers given underneath the elements, that's the average atomic weight, the average atomic mass of that element. And it takes into account all of the isotopes. Any questions?
You just took the percentage, multiplied it by 12?
The way we did that calculation, if you want to, if you care, remember a percent, you do a fraction and then multiply it by 100. That gives you percent. What we want to do for here is to simply convert the percent back to the fraction. So you divide by 100.
Fraction or decimal?
The decimal here. So 98.98 is the same as 0.989. And the same thing for 1.1% is this. Just divide the percentage by 100 to get back to your fraction.
Why would we do that? The process?
Well, you can't multiply by a percent
No, I mean, why would we go and do that with the formula?
because let's say we're going to do an experiment in lab, and you're going to weigh out carbon. And you want to know, you don't understand this concept yet, but you want to know the number of moles of carbon you have. That's the number of atoms of carbon. Well, it doesn't weigh 12, it weighs 12.01 because we have the other isotopes added in. If you look at the periodic table, it makes a big difference, it really does. So anytime you do quantitative chemistry, you need to use the average mass because it's always a mixture of isotopes.
So on this table, the average is on the bottom in
Yep.
red?
And this one too. Yeah, well, that's red, this is black, but whatever. Now you might wonder how in the world chemists do this. This is just for acute information. This is what's known as a well, it's a gas chromatograph and a mass spec. Now, what you do is you take your element or your compound, whatever, put it into the gas phase. You ionize it, make a beam of it, run it through a magnet. The heavier the particle is, the bigger this path is going to be, 46, 45, 44. And then you detect it over here. These things are just remarkable in terms of their accuracy. For example, these are isotopes of boron, boron 10 and boron 11. Boron 11, 80.2%, but look how accurately we can measure the mass for this thing. All of those are real significant figures. The mass spec is just a fantastic instrument, and that's how we do it. All right, you may have noticed that the more interesting periodic tables are colored. Now, sadly, the periodic table you get on your exam will not be colored. Okay, you could color it, but and some colored pencils. But the reason that many periodic tables are colored is that they're showing the different groups of elements. All of these guys that are in this bluish color are considered metals. Now, metals do things like conduct electricity. You can pound them out into thin little places. They're malleable. They have properties, they have bonding properties that you would associate with other metals. Over here we have a yellow group. These are the nonmetals. Nonmetals do not conduct electricity, and they tend to be very brittle, or gases, or whatever, or liquids. So metals and nonmetals. This is going to be a very important distinction to you, because this is going to define the bonding type in compounds. These guys at the middle, everyone's heard of semiconductors, right? These are the semimetals. They are at the borderline between conducting metals and non-conducting nonmetals. So silicon, germanium, antimony actually, boron, these are the semimetals. Within the periodic table, sometimes if you are reading, you will hear words used. I typically won't use these, but just in case you come across them in a book or something, these things on the ends, our bookends, are typically called the representative elements. Long, long time ago, it was thought that the representative elements were the things that were found in living things. Turns out they're wrong, because everything is in there. But these are the most common. In between the representative blocks, we have these things. They're metals. They're called the transition metals. Their chemical properties actually transition from these to these. Now, you may wonder why these guys are stuck down here at the bottom. Well, turns out that they actually fit right in here. So if you open up your table, cerium comes right after lanthanum, thorium after actinium. So they fit in here and complete those rows. So it actually would look like this. Now the problem is that this is a stupid periodic table. You could never hang it on the wall, could you? And since nobody really cares much about these elements down here anyway, we just kind of take them out and put them at the bottom. But that's why they're there. This is where they really go. The group 8s are what are called the inert gases. Inert gases because they don't react with anything. Now, actually, they do, but they don't react easily. They, kind of kick and scream all the way. The ones next to it are very important to you. Make sure you know these guys, the top 4 here. Those are the halogens. They are very, very common, very reactive. We will use these guys all the time. Same thing with these guys over here. We've already seen lithium, sodium, potassium. These are the alkali metals, is what they're called. Alkaline earths are the one next to them. Again, it's old nomenclature, but you will see it in the book. Do all periodic tables look like this or this? No. This is one of my favorite odd ones. Don't ask me to explain exactly how it comes about, but it's a very strange periodic table based on the same principles. Any questions? Well, let's do a couple quick exam problems here. We have phosphorus with an atomic number of 15. Mass number is 32. How many neutrons? Remember, mass number is simply protons plus neutrons. This is 17 neutrons. Then we have bromine. Now, this is a neutral element. How do we know that? Because if it was negative, here after the element symbol would be a -1. So there's no symbol, that means this is neutral. If it's positive, it would be +1, 2, 3, whatever. Negative, -1, 2, 3. But when there's nothing, it's neutral. All right, so what does it have? This is the atomic number, right? So it has, how many protons? 35. We're down to A, B, or C. Mass number is 79. 35 of those are protons. 44 neutrons. Oh, shoot. But if this is neutral, how many electrons must it have? 35.